Hello and welcome to the basic course for PLC of the latest generation modular platform MELSEC iQ-R by Mitsubishi Electric. In this basic course, we will deal with several topics inherent to the iQ-R system, with a focus in particular on the control PLC, therefore on the PLC-R, which represents the heart of the modular system. We will divide the course into three parts. In the first part, after a generic introduction to the iQ-R system, we will try to pay attention to the main rules of configuration of the system and the technical characteristics of the PLC of control. I was mentioning configuration rules. We will see how usefully a configuration tool exactly to take into account all these rules and how in fact it is necessary to represent a tool useful for defining the iQ-R needs of the machine. So if it is important to take into account the main configuration rules, it is also important to know that there is a tool that we can rely on to define your own hardware configuration without having errors. We will also talk about I/O assignments, so how the digital inputs and outputs are mapped and coded, and not only. So more generally, we will talk about I/O points based on their placement on the rack. The I/O segment address system will be basic on a numeric hexadecimal system. In the second part of the course, instead, the PLC programming environment called Gigsworks 3 will be introduced and presented. In this context, we will start talking about retrocompatibility with with the software projects made with the previous Mitsubishi programming environments. I refer to Gigsworks 2 or Gigs Developer. For previous modular PLC system, in this case I refer to the Q series. We will talk about programming languages contemplated in Gigsworks 3 based on the standard ISC 61.13.1.3. We will see the steps to create a new project, how it is possible to make a project upload present on the physical PLC. Clearly, in a programming environment, a programming environment is made up of a project tree. To understand the main window that we will find on the left of Gigsworks 3, and in this regard we will go to know the elements that characterize the tree. In a PLC software project, a configuration of the hardware with which it will then physically interface will be executed. Therefore, it will be shown how to make a hardware configuration in the Gigsworks 3 project. Next, we will talk about memories that make up the PLC-R, then the device label. The first, in turn, differentiated in user device, meaning programmable memories made available to the system, which therefore will not need a variable declaration, as they are already known and able to be used by the user in programming. For example, we will know the devices identified with the letter M, which will be devices for the Mitsubishi World device by bit, or the 16-bit real world devices identified in the Mitsubishi PLC with the letter D. So we will discover the device. We will discover D0, D1, D2, and so on. In addition to user devices, we will see system devices, that is special bits and word memories, to which the system assigns a univocal and not mutable meaning. We will talk about SM as regards special bits and word memories, and about SD as regards special bits and word memories. Next, we will talk about labels, the variables defined by the user in the PLC programming phase, each with a unique name. When we talk about labels, we will differentiate the local labels, so those locally defined in a programming container and consequently exclusively usable by itself, and the global labels. So globally defined in the project at a predisposed point to contain and define the global variables. For example, they will have to be defined in the project, so globally defined in the project at a predisposed point to contain and define the global variables. For example, they will have to be defined globally in the labels which will have to be put outside, put in communication with an operator panel. We will see how we will actually also talk about label modules, so labels associated with the smart modules present on the REC iQ-R present in our configuration. In this case, the GXWorks tree gives the possibility of adding these module labels with which to program an interface and also to define the local variables. As well as the devices, the labels can be of different nature. So for each of them, the type of data must be defined, for example, Boolean. So if the type of data is bit, a word at 16 bits, a double word at 32 bits, or a type of data, for example, a string. We will see how to do it in the declaration phase of the local variables. We will see how to do it in the declaration phase of the local variables. We mentioned the program containers. We can call them program organization unit. This will be put into operation by the PLC and therefore scheduled on the basis of the type chosen by the user among those available by the PLC scheduler. We will depend as much as possible in a basic course the different types of execution listed here. In the third part of the course, we will go into the part of programming PLC-R. So we will talk about project structure, how to create POW, how to create and store function blocks, how to create and recall functions, or how to create, for example, user structured data. Once the programming is completed, it is necessary to perform a code compilation. We will see how to compile the GXWorks tree project, or alternatively, how to perform a rebuild, or so a rebuild of the project if, for example, parameters are made and modified. These two operations to make sure that there are no errors for the compiler, so as to be able to download the project in the PLC. Once the writing in the PLC is done, it is important to know what are the main debug tools of the code, which are often used in the startup phase or application callout. So in the course of this, as the last debug tool, it will be enabled to the simulator. Therefore, an integrated function in GXWorks that allows you to virtualize on your PC the PLC, and therefore to be able to debug your program even before physically interfacing with the PLC. Finally, the manual viewer will be presented and an offline help containing complete digital manualism on iQ-R and more. It is good to highlight how important it is to keep this tool updated and how manual consultation is often helpful for the retrieval of technical information on products. The iQ-R system on the PLC Mitsubishi lineup is located at the highest point. This in terms of performance, therefore calculation power and backplane speed. And in fact, iQ-R is the evolution of the Q series and is even more performing than the latter. To give a data, the processing time of an elementary instruction in ladder for the iQ-R is below the nanosecond. iQ-R allows the complete integration of control and communication in a single hardware platform that makes it highly scalable, flexible, and modular. This is especially thanks to the wide range of I/O modules of different network GPU. Communication modules, communication for serial buses, such as the CAN-open and Ethernet, basic communication modules, the most widely used in the industrial field. This is what gives the possibility to do an iQ-R system, so it presents this wide range of products. It is also a multi-CPU system. So in addition to the control CPU, which we will focus on in this course, there is the possibility of integrating different CPU on different functionality in the iQ-R system with control functionality, not only specific ones. So you have a safety CPU. So according to the recognized international standards of security, SIL 3 PLE, the safety CPU allows the connection of security devices such as emergency arrest, door switches, and other devices through an industrial Ethernet-based network, CC-Link IETSN, the latest arrival, without the need for a dedicated separate network. So we will also talk about safety over Ethernet. A CPU of process containing algorithm dedicated to the process, which PID and not only, and with which it is possible to create a redundant system for an even more reliable control. So it is in fact possible to make a swap in a redundant system between two processing units. The second takes control compared to the first, from the moment when the first can have a functioning interruption. Process and security CPU SIL 2, according to the standard of the EC 6158, is used in a redundant system, so dual functionality. CPU motion is a special CPU for high-speed movements where important performance-related electrical axis to be managed. Let's say that CPU motion can handle up to 64 electrical axis. In a multi-CPU system, we can integrate a maximum of 3 CPU motion plus motion plus a control CPU. So it means that it can go to control in synchronism, for example, in the worst case in terms of motion impact, 192 electrical axis. This axis will be connected to the CPU in optical fiber. CPU robot, therefore, for the control of industrial robots. Also in this case, up to 3 units of robot control on a single rack. CPU C controller, which is in fact a multi-core controller based on an ARM processor with the pre-installed GXWorks operating system, and which supports the execution in real time of programs developed in C language, thus providing a stable and deterministic alternative to the two systems based on PC. What is the iQ-R system made of? It is made up of a rack, therefore of a main base unit of a backplane mounted on a DIN drive composed of n slots. There are different sizes of racks. I refer to the number of slots allowed. For standard models, a 3-slot rack can be chosen, a 5-slot rack, an 8-slot rack, and a 12-slot rack. If we take into account the rack of 3 slots, it means to have a slot first, understood as the one immediately to the right compared to the power supply. We will get there in a moment, plus other subsequent 3 slot free. So actually they are for a rack of 3. Understood as slot on which they can be housed. Therefore, CPU modules or smart modules or I/O modules are 3 plus 1. They are available as regards the power supply module. So we are talking about the object, the device. To understand, we said it is always found, the element on the left of the rack. There are different power supplies modules available, alternating voltage 100, 240 volts, or continuously 24. It goes from the sides, it goes from the smallest sides of 3.5 ampere to the largest of 9. As I said, immediately to the right of the power supply, there is always a CPU unit, one or more CPU units. It is possible to compose the system up to 7 extensions made up at the most of 64 modules. So in the case, let's say worse, bigger the iQ-R system is composed of a main base unit, so in a main rack on which we will find n slots, on which we will definitely find a CPU, a power supply. We can go to remote throw, let's say connector and dedicated bus located on the left of the rack. We can go to remote up to 7 additional racks, so for a total of 7 plus 1 modules. I mentioned the smart modules. Let's say that, so in addition to CPU modules, we will talk about smart modules, and we will distinguish them from I/O modules. In fact, modules of cards, so digital inputs and outputs, or digital inputs and outputs. All the other modules for us will be, for the iQ-R system, will be smart modules. We will see that these smart modules will be associated with buffer memory, so memories to which we can access in reading and writing through our control CPU. Among the many modules of different network present and contemplated in the iQ-R system, I can mention then the module for high-speed inputs, the module for output input strain, fast counters, modules for control inputs, module for serial communication, so with port 232, 422, 485. So for example, to manage a RTU Modbus, but also a MES module for direct interface with the commercial databases such as SQL, Oracle, or the OPC WAP server module. More and more requested, used in the manufacturing sector for interconnectivity and data exchange between various machines and devices on the basis of this language, Universal Protocol OPC WAP. An important concept that can be important for those approaching the iQ-R system, starting from a system, is a bit of a retrocompatibility discourse. However, of migration from Q to R, this can be done in order to follow, and respect some configuration rules. But what is the concept? What does it mean? It means that starting from a Q system, meanwhile a hardware migration to a R system must be made. This R system will be installed, mounted certainly on a main base unit, because we have said that in any case PLC can exclusively live have it within the main unit, therefore not on the extension, and on this rack we will eventually place other modules of the iQ-R series. At this point we can go on our new machine architecture, machine configuration. We can go and reuse modules of the Q series, but by hosting this of an extension RQ extension based unit, and an extension dedicated to the conversion between the R word and the Q word. It is then possible to make further entries on an extension at this point, an extension of the Q series. So in fact, there will be this rack that will be a bit like a gateway. So the migration from here to R can be done by respecting and accepting what we have just said. How does it look like? So let's talk a bit about the technical characteristics. How does our PLC look like? So our control CPU is a bit like a rack, and on the front side there are two we find two ports. One attached to contain the USB 2.0 port, usually using the Ethernet alternative to connect to the Gixworks tree, and another port up here, darker in color, under which we find the LEDs. Some LEDs referring, for example, to the battery status, to the state of execution of the PLC. So if in run, if in stop, if in error, and a slot to contain an SD card memory. This SD card memory can be used for the saving of data, such as boot files, comments, device data, file the log through the SD card. For example, it is also possible to update the firmware of the CPU through a few simple steps, or also possible somehow through a project programming, a Gixworks tree project configuration. We can download our project in boot format within our SD card, and then start the project, not by downloading from Gixworks tree, but by inserting the SD card with our project in boot format within the PLC. You can then extract the SD card, and the PLC will continue to execute the project without problems. This can clearly be convenient from the moment you want to install more than one machine. So you bring the SD card on the first PLC. It is removed. It is bring the SD card on the first PLC. It is extracted. It is brought to the second PLC, and so on, without the need to connect individually with the various CPU of the various machines. In this case, an example. Moreover, it is always present, remaining on the on the bottom RJ45 port, an Ethernet port compatible with CC-Link iField Basic, so with Ethernet-based bus of the CC-Link consortium at 100 megabit. The CC-Link iField Basic differs from CC-Link iField because the latter actually runs at 1 giga, so it certainly has performance in terms of hard real-time better. In this case, with this built-in port integrated, we can manage a master for CC-Link iField Basic, not for CC-Link iField. We'll see how to do it later. In iField Basic, in addition, we have therefore talked about the USB port, the RJ45 port, the memory card slot. On the left side, it is present starting from the R04 CPU, an additional port on which a memory can be housed, an extended SRAM, so additional one. We're talking about an optional one. We can refer to this extension from the moment when you want to extend the memory intended to contain the devices and labels, not the memory intended to contain the programs. So when we have to extend, I repeat, the memory, the device, the label, we can do it through this option. On the return of the RJ45 on the Ethernet port, in addition to CC-Link iField Basic, various protocol or types of communication can be integrated on that port. So that port can be exploited, for example, for connect with a GOT or with MailSoft product, and you can implement a communication based on SLMP, on Modbus TCP. You can integrate an FTP client or server function, a web server function. So in this case, our PLC that through that port goes to communicate through web browser, goes to communicate with a web client, or a communication called simple PLC communication, often used in the Mitsubishi world for data exchange, let's say between different PLCs, also of different families. So a PLC R could communicate through simple communication with an FX5. Finally, on the underlying part, which in this case we cannot see, there is an additional port that contains the buffer battery. Here, usually when it is recommended, the CPU, this battery is disconnected, so the CPU does not run, and a red LED appears on the relative relative LED dedicated to the battery state. It is remembered to open the port and to power, so they connect the battery via through a specific connector. Here I was mentioning a little to the topic of the accelerator SD card. Apart from the R00 will be extended from R04. Here we are anticipating what are the CUTs, the different CUTs of the CPU. So the R series, we are talking about the control PLC. This card, this control CPU can be an R00, can be an R01. In a moment we will discover all the CUTs and we will see what it means, what they fundamentally differ. Here we can see the different CUTs available for the air control CPU. So we start from an R00, we can then choose an R01 or an R02, an R04, an R08, and a R16, an R32, an R120. In fact, one of the aspects for which they differ is precisely the capacity, therefore the capacity of the memories dedicated to of the two memories. One, the first dedicated to contain the program, so we will talk about the program memory, and the second dedicated to contain the devices and the labels. So the difference is that, for example, for an R00 in terms of program capacity, we have a memory of 10 kilosteps, for an R01 of 15 kilosteps, for an R04 40 kilosteps, and for an R120 1200 kilostep. By bringing this data in bytes, we have a multiplicative factor of 4. So from 10 kilostep, we can also talk about analogies of 40 kilobytes. For an R04, for example, we can talk about 40 kilostep of program memory, or 160 kilobytes of program memory. As for the memory in which we go to memorize the devices and the labels, we have a capacity for R00 of 252 kilobytes up to 3,380 kilobytes of the largest CPU in Italy, the R120. They don't differ by the number of I/O points that can be managed. We will come and clarify these aspects of I/O points in a little while. However, in this case, they are identical or better from this point of view. There are no differences between the various CPU. They can also be differentiated a little as anticipated, as said in the previous slide, for hardware and software function. In this case, for example, the SD memory card is not present on R00, or the possibility of extending with the SRAM memory. The memory for the device label, this option is not present for R00, R01, R02. So in fact, the suggestion is, where possible, always start from an R04. Or however, make sure that the specific function required can and are also present on R00, R01, R02 if you want to opt for one of these three. Here is another important aspect that is good to talk about, the EN version. So for R04, R08, R16, R32, and R120, there is an additional version of CPU. So in this case, for example, we will talk about R04 EN CPU. But what does it mean? It means, in fact, having a CPU, a single module. So in a single case, a single device, two are actually integrated. So the CPU R04 in the case of R04N, and an additional module, which is the RJ71EN71, in this case an information module that carries within two additional Ethernet ports. Here in this case on one of the two additional ports, so of this expansion, we can go and manage a master if we link the fields to 1 gigabyte. So it's like we have two parallel options. Let's take for example R04. We can have a R04 CPU module next to which we can install a module information module RJ71EN71 with the two additional Ethernet ports. This configuration is similar to another one, which instead provides the only how to say the only inclusion of an R04EN. So R04EN is the result, the body of an R04 plus an RJ71EN71. As I said before, the CPU module is definitely the first mint like that immediately to the right of the R04N. So the CPU module is the first to be installed on a main unit. The first mint like that immediately to the right of the power supply. Does not exclude the possibility of installing up to 4 CPU. So for example, a control CPU and 3 robot CPU. In this case, the 3 robot CPU would occupy the first 3 slots, here identified with the numbers 0, 1, 2. The maximum number of devices manageable on an iQ-R system is 64. This number clearly goes to decrease the maximum number of CPU in the moment when, as I said, additional CPUs are introduced. On a rounded system, the maximum number is 11. As for the cable distance, for the extension we talked about before, the maximum distance is actually 20 meters. This distance goes down to 13.2 meters in the presence of modules of the Q series. So from the moment we have in our configuration, we have added a rack RQ. As seen before, in this case, the maximum distance is between the first and the last is 13.2 meter. If they have a restriction also on the number of modules mountable, for example, if we look at CC-Link IATSN module, which can be, for example, used to do as master, so as a master of the TSN networks, RJ71 GN11T2, the system tells us that at most they can be added integrated in the iQ-R system up to 8 of these modules for a configuration with a single CPU. In a multi-CPU system, so let's take as an example the case in which we have 4 control CPUs. So let's do a 4 multiplicate 8. We have at most 32 modules CC-Link IATSN. This is because each CPU can manage and control up to 8 modules. As for the combination between the main rack base and the expansion, in fact, all configurations are allowed. I will make you notice that for RB we identify the redundant power type, so rack for the redundant system, and with the HT extending temperature range type, so in the presence of a main based unit of this type, we can ensure the correct operation of the hardware no longer in a temperature range from 0 to 55, but from 0 to 60. Okay, looking at the lower part of the slide, we talk about combination of CPU modules in a multi-CPU system. Here, in fact, the combination between the various CPU are reported, first of all, in tabular format. In the meantime, we have talked so far about R in the version we have talked about before. For P, we identify the CPU of process. For MT, the CPU motion. For NC, the particular CPU for the numerical control. CPU RT, CPU robot. C are our controller C, SF the CPU safety. In fact, here we see that they are reported, they are columnized here, the CPUs that can be mounted in the first slot, so on the right of the power supply. In this case, let's say the only CPU that can be integrated in the system in an autonomous form are these. In the case, for example, a CPU, a control CPU R, we can have, for example, 3 additional CPU robots or 3 CPU motions, so 3 plus 1. But we can also create a multi-CPU system, for example, with 4 R CPUs. So this one subject and 3 more. For example, going back a little bit to the robot motion control configuration, in the case of the R CPU in particular, that robot, we see that already when we choose or we think of choosing a CPU EN, for this we cannot go and apply a CPU robot. So in fact, we have to go back to the configuration with an RN CPU. Let's look at the tool. Then our configurator tool. Our configurator MERSEC iQ-R series model selection tool. This can be used in an online form, so you can access it directly from the Mitsubishi portal, pre-registration, free, or you can download it and then use it in offline mode. Clearly, if we use the online one, we will find by default, we will interface with the version more and more updated. Here, meanwhile, our configuration tool is presented in a graphic form in this way as regards the main information that is reported. So in point 1, in fact, the configurator reports starting from the chosen power supply, what are the current absorptions. It warns us if, as we will see shortly, if the power supply is not sufficient. Number 2, the number of I/O available. So in this case, sorry, I was anticipating a bit the I/O points discussion. And we say that regardless of the size of the chosen CPU, the system contains a maximum of 4096 points. Here we are adding modules, but not only modules intended as inputs and outputs cards. We are adding points, but for any module more or less intelligent. Each of them occupies I/O points. The information is always reported in this box in the configurator. I/O address, so here in point 3, practically at the top, based on the occupied slot, we have an address in hexadecimal format. So if a card starts from 000F, if the first card installed, let's say, occupies 16 points, or from 001F, if the first card occupies 32 points, and then always in hexadecimal format in a continuous manner. The address are increased. Material list for any order, so in point 4 in this box purchase list, if you access this option, it is possible to view in printable format the module selected in the configuration just completed. 5 configuration details in configuration chart here at the top appear again in printable format, all the information related to the architecture, the configuration of the modules, the number of modules in the tool. If the maximum number of 64 modules is used, it will not be possible to add more modules. So as I said, the configurator knows all the rules of configuration. If the power supply of module is not enough, a message of error will appear. In this case, on the second extension, the power supply capacity is insufficient. For an error of this type, what can you do? You can choose a larger size power supply. If it has not already been done, or you can eventually add a larger size power supply. So you can add a larger size power supply to the added rack. Now let's talk about the I/O assignment. The I/O assignment is a very important part of the tool. The I/O address is assigned using a numeric hexadecimal system. The inputs are assigned to the X devices, the outputs to the Y devices. So in our system, when we go to the Gxworks tree, we will point to the inputs through the memory, the X0 input, X1 or XF, or similarly. We will use the memory, the y0 instruction, if we have to write the first output, or yf if we have to interface with the 16th. The address is assigned to an I/O module based on the assignment to the previous module, and the less significant number of the address of each module always starts with 0. In this image, we can see how a manual viewer works. Once opened, we go to select the manuals. Then we select our iQ-R and open network. Then TSN and select our module. Then in the appendices part, in I/O signals, and then in list I/O signals, we go to see the inputs and outputs associated with the module. Here, in the presence of extension, the concept extends and remains analog. So we go to the extension base module, the I/O number, and we start from the next number to the last I/O number on the main base module. So from 44F we go to 55F. Each slot on the base module has a number of I/O corresponding to the number of points of the module. With this, we have concluded the first part of the course. Thank you for watching.